So with that PCAM model in mind, I'd like to drill down into the P part, the partitioning part, and look at some common mechanisms that we use to partition programs to run in parallel. Here's a diagram that gives us kind of an overview of this. So the partitioning can be done in several main ways. We're going to look at two of these called functional partitioning and domain or data partitioning. Another word for partitioning is decomposition, but that's sort of macabre, so either way. Functional decomposition is the idea of taking the functions that the program does and splitting the functionality up onto multiple processors. So the different processors could conceivably be running either different code altogether or different functions within the same program. And the parallelism is going to come because you have the ability to do multiple steps in the process simultaneously. In contrast, domain or data decomposition or partitioning has to do with splitting up the data into multiple parts so that different processors can operate on different pieces of the overall data set simultaneously. This is what we saw in the example of the convolution, where we split up the image into different subsets of the overall collection of pixels and had multiple processors operating on those subsets at the same time. This is also the case for earlier examples like list minimization and that kind of thing, where we split the data up into subarrays, found the smallest value in each of those subarrays, and then combined those smaller values in a final step to come up with the global minimum. All right, so we're going to first of all delve into task parallelism, which is the linear version of functional decomposition, as you can see here. The idea here is that we're going to have interoperating tasks that are going to, in total, solve the overall problem. This is a kind of a contrived example here where we're imagining that if we're, say, designing a game, a computer game, that we're going to have different kinds of functionality that's going to have to take place in that game more or less simultaneously. For example, we're going to have to keep an eye on what the user's doing. We're going to have to be able to update the display. We're going to have to play some sounds, sound effects, music, whatever. And because we're going to imagine that we have a non-player character, we're going to also have to do some strategy that needs to take place in order for the NPC to do its thing. Now, these things are all parts of the overall implementation of this game, and you can see that we've obviously split apart the tasks that need to be done in that game, and we can allocate them to different processors so they can basically continue simultaneously. We could imagine a sequential implementation of this that just iterated over this loop very rapidly and did a little bit of each one, but if we have multiple CPUs at our disposal, which of course we do in modern gaming engines or PCs, we might as well do them in parallel. So this is a very simple schematic view of what that might look like, where we're going to split it apart. And again, we're talking about task parallelism. So I've listed these little task ideas here where I've got 4 different tasks. And inside those tasks, rather than doing all of those 4 main steps, we're just going to focus on one thing. So task 1 is basically just going to loop over user input. Task 2 is going to worry about screen drawing. Task 3 is going to be doing sound and music. And task 4 is going to be the AI behind the non-player character. I've also just kind of, again, schematically shown that each of these things is going to have to do some sort of a barrier operation so that they can kind of stay in sync over the time that the game is operating. So a barrier basically means it's a place in your code where you get to, and you can't exit that barrier until all of the other tasks get to a similar place. So we don't have to worry in this kind of an implementation about one thing getting done before another thing as we iterate through each of these tasks that need to be done in parallel to keep the game going. We just sort of wait for the other guys to arrive at this barrier, and then we go on to the next step or the next tick or however you want to look at it. But again, the key thing here is that each of these parallel tasks is doing some part of the overall problem, the overall algorithm. They're not necessarily partitioning the data exclusively. It's the functionality that's being done in parallel. Next, we'll take a look at the recursive approach to functional decomposition, and this is usually called divide and conquer. And something that we're familiar with from sequential algorithms, so the example we'll use here is our friend merge sort. And the basic idea is similar to a recursive algorithm on a sequential machine, right? You're going to take the overall problem and then you're going to split it into smaller pieces and solve the smaller pieces and then combine the solutions to the smaller pieces to come up with the solution to the bigger piece. And of course, that's a recursive definition. So as you split the problem into smaller pieces, you could split those problems into smaller pieces and so forth. Here, however, we're using this as a strategy for problem partitioning or problem decomposition. So rather than strictly thinking about partitioning the data only, we're also going to think about how do we allocate new processes or processors as we're going through this decomposition process. So we're going to basically split the problem into smaller pieces and delegate those smaller pieces, the sub-problems as I've shown it here, to additional processors. We're essentially generating tasks kind of dynamically at runtime, as opposed to the task model that we looked at back here, where these are fixed tasks that are running for the entire duration of the program or the entire duration of the game. In this case, we're coming up with these subtasks dynamically based on the shape of the data, the number of processors available, and so forth. Of course, when we're doing recursion, we need to have a base case, a condition that we can identify that tells us when it's time to stop recursing and unwind back to the top level caller. And in our case here, the base case is going to be when it's no longer worth it to allocate a subproblem to a new process. We know from past experience already that creating a new process or a new thread is not a free operation. It takes some time. It occupies some resources. So at some point, you're going to kind of get diminishing returns where you try to spin up a new process or a new thread, and it's not worth it to do that because the amount of data that remains is too small. So the base case basically is when we run out of work to do or enough work to justify spinning up another subprocess. To refresh your memory, this is what sequential merge sort looks like. It takes an array A, and then each of the calls gets two values that give us the indexes of A that specify the range of values from that array that we're responsible for sorting. The termination condition is determined by the relative size of end and start. When the end actually exceeds the start, as we call ourselves recursively, that signals the fact that we don't have any work left to do, and so we'll unwind the recursion. If we do have values that need sorted still, we'll take the middle of those two endpoints, the start and the end, and use that as a way to partition the array into smaller pieces. That's the fundamental nature of a divide and conquer algorithm, is that we're going to solve a larger problem by splitting it into smaller problems. And that's what takes place here with these two recursive calls to merge sort. They're both going to take the same array A, except now we're going to send in different indices. So the first recursive call will sort of the left-hand side from the start index to the middle that we just calculated. And the second recursive call will sort from the middle plus 1, so we're not duplicating that, through to the end of the partition that we were passed at the beginning of this recursive call. After those recursive calls return, we need to do a merge. This is the conquer part of the divide and conquer algorithm. The merge lists function is supposed to take the sorted sublists that were created by the two recursive calls and then combine them together into a single sorted list that extends from start to end in array A, and it needs to know that middle value as well, so it knows kind of where to start looking for the next value in the sorted sequence. So that should be familiar to you, and now we want to see how do we partition this in a divide and conquer approach for task partitioning. Think about what's going on in that recursive algorithm. This illustrates kind of the call graph. So this MS here, you can see MS refers to merge sort. When we start out, this example just shows the sorting of an array A that has 8 elements in it. So from index 0 to index 7. So the first call, or the 0th call as we're showing here, is going to partition that list into two smaller lists, and then if we can follow the index numbers here, the first recursive call to merge sort is going to sort, again, it's all going to be array A, but it's going to sort from indices 0 to 3, and then the next recursive call is going to sort from indices 4 to 7. And then those in turn will call themselves recursively to sort the different pieces and parts. And then as the recursion starts to bottom out, you can see here at these leaf nodes, we've got the calls to the merge list function that are combining those lists on the way back up the tree. And eventually we'll come all the way over here to step 21, where we're merging the final sublists that were partitioned at the first call to merge sort, and that yields the result from the top level call. So far, we haven't really said anything about how we're going to use this divide and conquer strategy to parallelize the execution of the sort. We still are going to have to eventually call these same functions that we're illustrating here in the call graph, but we want to think about what processor or what thread is going to do the work for those things. And this other illustration, the dependency graph, kind of shows that. Remember that the idea here is to dynamically partition the work into smaller pieces and give each of those smaller pieces to a separate processor so that it can progress in parallel up to some limit where we either run out of processors or we don't have a big enough problem to justify starting up a new processor. So at the very beginning, we're only running one task or one process or one thread, however you'd like to look at it. And that's going to be basically started with the original call to merge sort. When it's preparing to make those recursive calls, it's not only going to just call itself recursively, it's also going to decide whether it's worth it to spin up a new process. And here I've illustrated that that's taking place in the first level of the recursive calls, where now we're going to create two tasks. One is going to get this work, and the other is going to get this work. And then just again for illustration, it turns out that those two tasks are themselves going to decide it's worth it to do a partitioning and start up two more tasks that are going to do, in this case now, those two tasks are going to do the sort of their particular partition and do the merge, and then return the results back to the two tasks that started the four tasks off. So when this task completes and this task completes, they're going to send their values back to this task, which is then going to merge the two sublists. When these two top-level tasks return back, they're going to send their results to the original invocation processor, and it's going to merge together the sublists that they came up with. So same algorithm, same call graph essentially, but we're figuring out how do we use multiple processors to execute non-overlapping subsets of the overall work in order to speed things up. All right, let's turn our attention now to the data decomposition or domain partitioning strategies. And the first of these that we're going to look at is the geometric decomposition. This is actually something that we've already seen. We used it for the convolution examples. So a more general purpose definition of geometric decomposition is basically partitioning some linear structure that could be a multi-dimensional structure, so an array, a 2D matrix, a 3D matrix, an image, whatever, along one or more dimensions. And the convolution example that we just worked through is a great example of this geometric decomposition. The first approach that we took was to split it up by giving individual pixels to the processors. And then we backed off from that, partitioning it into vertical bands of pixels, each of which was given to a processor in the multicomputer. So the partitioning, again, is a data decomposition. We're splitting it up in terms of the geometry of the problem. In this case, a 2D array split into sort of smaller 2D arrays, which were given to each of the processors. And finally, let's look at recursive data decomposition. Again, we're decomposing by the data, but in this case, we're thinking about problems where there is no obvious geometric kind of partitioning for the problem. Here's a generic definition for this. We're going to decompose the problem into either individual elements or groups of elements that are each going to be assigned to a processor. And we're thinking particularly about problems where geometric decomposition is not useful. Geometric decomposition is useful in a ton of problems, but not every one. It turns out that in this case, we may have to modify the serial algorithm to allow for it to execute concurrently. And we're going to see an example of that here. In a way, this is kind of the parallel equivalent of dynamic programming, right? Dynamic programming allows you to sort of solve problems recursively and reuse the solutions to previously solved subproblems to combine together into the overall solution. And we'll see how that falls out here as we look at an example. The particular example we're going to look at is called the calculation of partial sums, and this is the definition of it. We're going to start out with an n-element array A, and we're going to compute the partial sums of A into an n-element array called S. Now, a partial sum is basically tallying up consecutive values of array A and summing those values and storing the results in array S. So here's a little simple example. We've got our input array A and our output array S. And the first value is just going to be the sum of A of 0. And then we're going to add to that A of 1. So 2 plus 3 gives us 5. We're going to add to that A of 2, which gives us 5 plus 5 or 10. 10 plus 7 is 17. 17 plus 11 is 28. So S is the partial sum, or contains the partial sums of array A. It's partial in the sense that it contains the sum of all the values from A up to a certain index. So the partial sum here at index 0, 1, 2 is the sum of the elements of A from element 0, 1, and 2. And the formal definition of this is straightforward. We're basically just saying the sum at position I, index I in our example, is equal to the total of all of the elements of A from index 0 up through index I, and that's exactly what we just calculated. Now, it's pretty straightforward to convert this into a simple sequential algorithm. We can start off with our base case here of the sum of the 0th element is going to just be the same as the 0th element of array A, and then go from index 1 up to index n minus 1 and make the sum of I equal the sum of I minus 1 plus the value at A at that index. And of course this has linear time complexity. You might pause the video and convince yourself of that fact, because that's going to come back here in a minute. Here's a different algorithm for doing this same problem. I'm calling this algorithm B. The previous one I've called algorithm A. I didn't mention that before. The idea here is that we're going to calculate partial sums over increasingly long spans of the array. You can see here that just kind of look at these arrows. We're in the first iteration here, we're spanning one element of the array, and then we're spanning 2 elements, and then we're spanning 4 elements, and then we're spanning 8 elements, right? You can see the pattern. It's kind of powers of 2. In the first stage, we're just basically adding adjacent elements. So into the value at index 1, we're going to add A0 and A1, and the result is going to be that that first element is going to contain A0 plus A1, which is the partial sum for that particular index in the result. Of course, the original value in A0 was already the partial sum of just that one element. So now, at this point, we've basically succeeded in calculating the partial sum for those 2 elements. But we've also been kind of teeing up values that we're going to reuse later. So for example, these 2 guys got added up, and we ended up with A3 plus A4 in this cell, and on down to A7 plus A8 in the final position in the array. Now we're going to increase the span that we're going to use for the next iteration. So you can see again from the arrows that we're going to add A0 into the sum previously gathered for A1 plus A2. So we're skipping over 2 elements of the array, and the result of that is going to be A1 plus A2 plus A0, which is the same as A0 plus A2. So at this step, we've calculated the final value for that element of the partial sum. And because we're also going to do a similar thing where we're going to skip 2 from A1 to A3, we're going to add A0 plus A1 plus A2 plus A3, which gives us A0 plus A3. So again, we're getting these spans of 4 elements that have now been given proper values, as opposed to just 2 elements in the previous iteration, or 1 element up here. And then we're going to do that again. So the sums that we're going to do in this next iteration, we're going to skip basically 4 elements, and we're going to bring in A0 and A1 plus A4 and come up with the value for A0 plus A4. And similarly, A0 plus A1 is going to be added to A2 plus A2 up through A5, and that's going to give us A0 through A5, and so forth. And then by the time we're here at the last step, we've now calculated the partial sums. That's the sums up to 0, the sum up to 1, the sum up to 2, and so forth through to the sum up to index 8 of the original array. Here's the basic schematic of a sequential implementation of this algorithm. You can see that we've got a step count. This is basically just the number of elements that we're going to step across as we're iterating through the arrays. And we're going to start at 1, which corresponds to this first stage. And then as we go through each of the steps, we're going to double that value. So we'll go to 2 and 4 and 8 and so forth, like we've seen back here. And our outer loop is going to continue to double that step count until we run out of elements that we're trying to partial sum. Within each of those outer iterations, which correspond pretty much to the individual arrays illustrated in this diagram, we're going to have an index called pos that's going to be used to figure out which elements of the previous step we're going to add together. So if we look here at the interior of the inner loop, we're seeing that we're going to have a new value at pause plus step, which is basically going to be the right-hand end of these arrows here. That's going to be the old value at pause, which was the left-hand end, plus the old value at pause plus step, which is the right-hand end of the arrow in the previous iteration. So having completed that iteration of the partial sum, we're going to increment pause by 1 spot. And that corresponds to what's happening here in the diagram, where from the position that we start doing the partial sums, we're always going to do a similar partial sum at the next element over until we get to the point where that would result in us trying to write a value that's in a position that's larger than our array. And that's how the termination condition works in this interior while loop. As long as pause plus step is less than n, we keep doing this. But when it gets larger than that, that means that we've done all of the partial sums that we have to do on this iteration. Again, compared to algorithm A, we want to think about the time complexity here. Turns out that this is order n log n. I would, again, encourage you to maybe stop the video right now and look through this and convince yourself that that's actually the time complexity that we've got here, and answer the question kind of why. So why did I bring up these two different algorithms? Go back and compare the time complexity. We saw that algorithm A runs in linear time on the number of elements in the input array, and algorithm B runs in time n log n. So algorithm B seems on the surface to be strictly worse than algorithm A. So why do we care? Why are we bothering with algorithm B? Well, it turns out it's fairly straightforward to parallelize algorithm B. In particular, each of the iterations of the outer loop here can be given to different processors. So all of those n steps can be done in parallel. Now, if we have a really capable parallel computer, that means we can do this really fast. If we have p equal to n, that is, we have n processors in our multicomputer, we can now compute the result in log n time. And that gives us a pretty substantial speedup, right? If we think about the speedup calculation, it's t sub 1 divided by t sub p, and here n is just equal to p. So this speedup is going to be on the order of n divided by log n, which is considerably better than order n. Now the downside of that is p equals n is a lot of processors for everything except a very modest input array. So the question becomes, can we make do with fewer than that? Can we do with less than n, maybe much less than n, and still see some amount of speed up here? Well, there is a detailed analysis in the reading that you're assigned for this section of the course, but it basically shows that the speed up on P processors is going to exceed the speed up on 1, or actually the runtime on 1, right? Because the speed up on 1 is going to be 1, when P is about equal to log n minus 1. So just to put some specificity around that, if we have 2 to the 20th elements in the array we're trying to come up with a partial sum of, that's about 1,000,000, right? We're going to need to have P be at least log the base 2 of 2 to the 20th minus 1, and this is just 20. So we're going to have at least 19 processors to get our speed up to be greater than 1 on P processors. Anything above that is going to increase the speed up accordingly. One final thought about this particular decomposition. Remember that we've got two different algorithms, and as soon as we start comparing two different algorithms in terms of measuring their speed up and the performance and that kind of stuff, we're sort of comparing apples and oranges. You might think initially that the way to do the experimental work on this particular approach is to uniformly use algorithm B, whether it's on a single processor or on multiple processors. I would caution against that. When we're calculating the performance of a parallel algorithm, we always want to compare it against the best known sequential algorithm. That's the way we get kind of a realistic estimation of whether it's worth it, in some sense, to parallelize the underlying algorithm. And in this case, we've kind of looked at some of the analysis here that suggests that there is a break-even point above which it makes some sense to parallelize this or to run the algorithm on a parallel computer. But that's part of the process of determining the value of using a particular parallel formulation, is when is that break-even point going to take place. So for this algorithm, if we were going to do experimental work on this and come up with speed up and efficiency curves and so forth, we would want to run the best sequential algorithm on one processor, and then the parallel formulation, algorithm B here, on multiple processors. Because we would actually like to see the fact that compared to the single processor best case, that for a certain range of processor counts, that is, in this case, for a million values in the input, for values of p less than 19, we would actually see probably a speed up below 1, right? We would be doing worse on the parallel algorithm because of its inherently increased complexity, but at some point we would hit a break-even point. And that gives us information about whether or not this is the appropriate parallel algorithm to use for a given problem. If we know we're always going to work on data sets that are larger than 1 million elements, then it probably makes sense in this case to use algorithm B on a parallel computer. But if we're only ever going to work on data sets that are less than 1 million elements in this case, it doesn't make any sense at all to use a parallel computer because it's going to be slower than just running it on a single processor using algorithm A, the better algorithm.